In this lesson, we're going to take a look at how the model of the atom has changed from Rutherford's atom and Bohr's atom up to the modern atom. There's a lot of math and stuff that we are not going to get into a lot, but hopefully by the end we can describe the 4 quantum numbers of an electron and kind of figure out how to describe where an electron is located in an atom. So this is a summary of Bohr's atomic model. Remember, we've got the nucleus in the middle. Electrons orbit in circular paths around it, and it takes a specific amount of energy to move an electron up, or an electron emits a certain amount of energy to fall down. That extra energy is emitted as light, and the frequency or color of light tells us how much energy the electron lost when it fell between energy levels. Now, Bohr's model didn't tell us why these different energy levels existed, just that they existed, and Bohr's model also couldn't explain the spectral patterns emitted by atoms with more than one electron. So some more refinement was needed, and that came from the French chemist, physicist Louis de Broglie. I don't know how to say that, I'm not French, when he said, well, let's take the wave-particle duality from light and apply it to matter. So instead of thinking of electrons as particles that orbit the nucleus, we're going to think of electrons as waves, standing waves that vibrate in circular patterns around the nucleus. And since only certain wavelengths can form standing waves, this is why there's quantized energy. This is why there's certain energy states. So this was a cool idea, and pretty soon after he proposed it, there was actually laboratory evidence to back it up. It said, yep, in fact, electrons can act like waves. So remember, when we have waves that collide, we get a cool interference pattern. Over here on the right, we see when two waves collide, we don't just get this constant ring anymore. We've got these areas where they have a higher peak, where the two crests come together, and then a lower or dead spot where a crest and a trough come together. And so if you think of an electron as waves, what we expect is to see this pattern when an electron source, something emitting electrons, is shined through a double slit pattern, because the two waves will start to interfere with each other, and you'll get areas of constructive and then destructive interference. So when you try this with electrons as particles coming through here, at first when the particles come through and they detect, you get what looks like a random pattern, like it's not wave-like at all. But as time goes by and more and more electrons come through, this does show that these particles are not hitting randomly. They are hitting in a wave interference pattern. We get these stripes of electrons appearing on the end, which says, yep, electrons are acting like waves. So now we've shifted our thought and saying, well, let's not think of electrons as a particle orbiting the nucleus, but rather as a wave that vibrates around the nucleus. And de Broglie said the way we actually get that wave, its wavelength, is by taking Planck's constant and divide it by the momentum of the electron. Mass times velocity is momentum. Well, that's all well and good, except that Heisenberg said you can't do that because you can't know both the position and the momentum of an electron, because the very act of measuring that changes it. The photons that hit the electron to measure it, to observe it, are going to change its position or change its momentum. So we can figure out kind of where the electron is, but then when we do that, we won't know its momentum because we've changed it. Or we can figure out its momentum, but then we won't know where it is because we've changed that. So we can't know both its position and its momentum, which means we don't know where a particle is or is going to be at every point in time. Like in classical physics, if I throw a ball, I can predict where it's going to land based on the conditions it has at the beginning of that throw. With an electron or a quantum particle like this, we can't do that. We don't know enough information to actually predict where it's going to be at any point in time. So we need a new way of dealing with this. And so Schrödinger and Max Born developed the idea of the quantum mechanical model of the atom, which extended this idea of wave behavior into 3 dimensions and then put it back into a particle. So Schrödinger said, well, let's not confine these electrons to moving in circular waves around the nucleus, but rather as a 3-dimensional wave form around the nucleus, a wave function. And so he developed the mathematics to describe this wave function, this 3-dimensional standing wave around the nucleus. And then Max Born said, yes, that, except an electron is actually a particle, And so we're going to think of it as a particle, but because of Heisenberg's uncertainty principle, we don't know where that particle is, but because your wave equation limits where it can be, we're going to say that your wave function describes the probability of where the electrons are likely to be found. So Schrodinger's wave equations, his wave function, describe the probability of finding an electron at a certain spot by the atom. Sometimes that probability is 0, sometimes that probability is high. And the shapes of the higher probabilities are called the orbitals, and orbital shapes describe where electrons are likely to be found around the atom. So we're going to go through the 4 quantum numbers that describe an electron's position around an atom. The first 3 have to do with locating the electron in an orbital. The last one, the last quantum number, actually tells us something about the electron intrinsically. It has to do with the orientation of the electron's magnetic field. So first we've got this model that looks a lot like Niels Bohr's model, but we've got these increasing energies. So basically this principal quantum number is telling me approximately the distance from the nucleus to a shell where orbitals are found. So the first shell is fairly close to the nucleus. It can only hold 1 orbital. The second shell is further out. There's more space there. It's going to hold more orbitals. The third shell is even further out. It can hold even more orbitals. And generally speaking, the farther we are from the nucleus, the more energy the electron has, because the more energy it can emit as it falls to a lower energy level. Sometimes that's not the case. If you've got a whole bunch of electrons blocking it, there's some shielding that happens. So occasionally there will be an electron that has higher energy in a lower principal quantum number. We'll talk about those when we get to them. Now, the next thing, once we've established the distance, or the principal quantum number, is we have to describe the shape of the orbital that's at that particular distance. So first we get its principal quantum number, then we get its angular momentum quantum number, which is called L. And like I said, L describes the shape. There are 4 shapes that we're primarily going to deal with. There are more than this, but we don't really need them. The first shape is a sphere. The second shape is a dumbbell. The third shape is a cloverleaf. And the fourth shape is a funky looking thing. I'll show it to you in a minute. The orbital, the shape, is called a subshell. So the shell tells me the distance, the subshell tells me the shape, and for a given principal level, or given n, the L values can be 0 to n minus 1. So if n equals 1, L can be 0. If n equals 2, L can be 0 or 1. So that tells me right there that the second principal energy level, or the second principal quantum number, that second distance, the second shell, can hold 2 orbitals. The third one can hold 3 orbitals. We can have 0, 1, or 2. And then the fourth energy level, or the fourth principal number, would hold 4 different orbitals. Like I said, the s orbitals, that corresponds to an L value of 0, are spherical. The p orbitals, which correspond to an L value of 1, are dumbbell shaped. The d orbitals, which correspond to an L value of 2, are cloverleaf shaped. And the f orbitals, which correspond to an L value of 3, are complex shaped. We'll look at those in just a second. So the s and p orbitals. Okay, it turns out that there's another quantum number that's needed to actually describe these orbitals, because if it's not a sphere, it can be leaned over or tilted and put in a different orientation, and that changes the orbital's position or orientation, which means we have to describe it with another quantum number. So when you have a quantum number 0, you have a sphere. This is an s orbital. When L is 0, you get a sphere. But when L is equal to 1, there's actually 3 orientations possible, because this dumbbell can be oriented horizontally on the x-axis, vertically on the z-axis, or horizontally on the y-axis. There's 3 orientations. So the p orbital actually consists of the same shape oriented in 3 different ways. The d and f orbitals are going to do similar things to that. So the d orbital has this cloverleaf shape that can be oriented in 5 different ways. Now, you'll argue with me on this one a little bit and say it's not the same shape. That's true, but it is a solution of the wave function there, so it counts. Same down here, we've got this 7 ways to orient the f orbitals. Okay. Now, the last quantum number is actually called the spin quantum number, and it tells me about the magnetic field of an electron. And why an electron has a magnetic field is beyond our scope, but an electron can orient itself to have a magnetic field up or down. They call that spin up or spin down, or spin plus half or spin minus half, which tells me there's a way to distinguish electrons within an orbital, which is good because an electron can actually be completely described by its 4 quantum numbers. Its principal quantum number, how far it is from the nucleus, its angular momentum quantum number, which tells me what shape its orbital is, its magnetic quantum number, which tells me what orientation that shape is in, and then its spin quantum number, which tells me about its magnetic field. Now, no 2 electrons orbiting the same nucleus can actually share the same set of quantum numbers. This is called the Pauli exclusion principle. And what that means is we know that there's only allowed to be 2 electrons in the same orbital, because if they're in the same shell, in the same orbital, and have the same orientation, that's the first 3 numbers the same. In order for their last 2 numbers to be different, there's only 2 choices, so there can only be 2 electrons. Okay, so only 2 electrons can occupy any specific orbital. So like the p orbitals, there's 3 of them. Those 3 orbitals can hold 6 electrons, but the s orbital is just a single sphere. It can only hold 2 electrons. This is that whole thing summarized. So the principal quantum number, n, which has values from 1 to infinity technically, although we'll probably never see anything beyond 7, tells us the general region for the electron. Then the L quantum number is the angular momentum. That tells us the shape of the orbital, or the subshell that it's in. So we don't generally think of these as numbers. We think of them as the shapes, and the shapes get letters S, P, D, F. If we need more than that, there's G and H, but we usually don't. The magnetic quantum number tells me the orientation of the orbital. And then finally, the spin quantum number is the direction of the quantum spinning of the electron. It's called spin because initially people thought it was actually something to do with the electron rotating, but it's not. There is no neat way to describe spin except that it has to do with the magnetic field of the electron.